Hello everyone, and thank you for joining us. The journey towards powerful quantum computers will traverse many challenging obstacles. How can we accelerate our progress as we're moving towards this quantum future? Today I want to tell you why integrating quantum and classical processing is so critical as we're thinking about this question obsessively at Quantum Machines. And I want to tell you how at Quantum Machines we're pushing this integration to new limits via our quantum control stack. So today in quantum computing, we're seeing two critical parallel efforts, which I call here the two races of quantum computing. The first race is the race towards quantum practicality, which focuses on demonstrating the value of quantum computing in the near term on NISQ processors. And this race is, of course, very important because only by showing the real value of quantum computers in the relatively near future can we continue to push the field forward with more and more resources directed to it. Now, the second race is the race towards fault-tolerant quantum computing. This race focuses on implementing quantum error correction successfully, and this race is, of course, critically important because only by running quantum error correction successfully will we be able to realize the full-blown potential of quantum computing in the long term. Now, it turns out that in both of these cases, the tight integration of classical processing into the quantum computing stack and the ability to program both quantum processing and classical processing together in a productive way are key elements for maximizing how fast we make progress. So quantum classical integration is like a super strong turbo engine that can push us along this axis and make us move faster. And if we don't build this engine right, we're going to move very, very slowly towards our goals. So to understand this, let's take a high-level sort of a bird's-eye overview over the quantum computing stack. So the stack includes four major layers, which are the quantum processors or the QPUs, the control hardware, the control software, and then the application layer, in which I also include higher-level programming languages and development tools. So the QPU is where the magic happens, right? This is where we have the qubits and the entanglement, and this is what actually is running the quantum processing eventually. Now, the control hardware is what drives the QPU and orchestrates the entire quantum computing program. And it has two main components. So first, we have the analog frontend, which is the interface to the QPU. This is what generates the analog signals that are the physical form of the quantum gates and measurements. And then we have the quantum controller, which is the brain of the control hardware. So the quantum controller generates and orchestrates the program. So for example, it says, now play this pulse to this qubit, now place this pulse to this qubit, now apply these measurements to these qubits, and so on and so forth. And this all needs to be done in real time in a very precise timing controlled manner. And then the interface to the quantum controller is a pulse level language that lets us define exactly what the control hardware does. So again, program, now play this pulse to this qubit, now play this pulse to this qubit, and so on. And it is then the control software that is responsible for the calibrations that run on top of the pulse level language and calibrate and optimize the native gates of the machine. And then the compilation, which translates programs from an abstract gate level language all the way down to pulse level language so that they can be executed on the machine. So the interface to the control software is, of course, a gate level, these abstract gate level languages that are out there. And then we can run applications. Now, quantum error correction is also today being developed and being explored right here in the control software part. And once we have quantum error correction, as I mentioned, we can move to the regime of fault-tolerant applications. We can run the most advanced applications. Okay, now, so why is quantum classical integration so important? Well, it's really required in almost every component of the stack. And I want to give you a few examples now. So first, if we look at calibrations, then in calibrations, we typically scan some parameters of pulses that we want to send to the QPU, and then we measure the results of sending these pulses to the QPU. And then we need classical processing to analyze these results and find the best parameters of the pulses that perform the wanted quantum operations or the quantum gates. So you see, classical processing is really interleaved with quantum processing here. We run something on the QPU, change the parameters of the pulse, then analyze the results, and then we do it over and over for many calibrations. So during these complicated calibration graphs of a quantum computer, we always run quantum and classical processing very much interleaved. Then if we look at quantum error correction, in quantum error correction, we need to perform what's called mid-circuit measurements, that is measuring some of the qubits in the QPU while the circuit, the quantum circuit is running. And we need fast classical processing to analyze these measurements and infer the errors and how to respond to these errors, and all during the runtime of the quantum circuit. Okay, so here we really need tight integration of classical processing, because we do this classical processing while the quantum program is running, while the quantum circuit is actually being applied to the QPU. Okay, now finally, if we look at the applications, well, most of the NISQ applications are variational algorithms that heavily rely, in fact, on classical processing to optimize a certain cost function of interest over parameters of a quantum circuit. So again, we parameterize the quantum circuit, perform quantum measurements, and then we perform classical processing to update the quantum circuit parameters until we minimize the cost function. So again, interleaving quantum and classical processing. So we see that in all of these classical processing tasks, all of those classical processing tasks are really interleaved with the quantum processing tasks in various components along the stack and for various reasons. And there are many other examples. And in fact, those various classical processing tasks must require, or they could require, various amounts of classical compute resources. So for example, for quantum error correction protocols, sometimes we need a super fast response for quantum measurements, as I mentioned, that could be done in hundreds of nanoseconds in the quantum controller itself. This classical processing has to run in the quantum controller itself. While maybe for variational algorithm, we may need access to heavier classical processing like CPUs or GPUs in the data center, in the cloud, or maybe even in an HPC. And so actually, the more we move away from the QPU towards heavier classical processing, processing resources, the more we pay for the communication time, the communication overhead. So it's really critical to build a hierarchy of classical compute engines in the right way to allow for to achieve the best performance. So this is kind of like with cloud and edge computing, right? We want this hierarchy of classical compute engines all the way from the cloud, all the way to your cell phone or your laptop, so that we can run the right classical processing in the right place in the stack. Unfortunately, this is not yet working well. Okay, so in many cases, calibrations take too long, which leads to increased downtimes and decreased performance. In many cases, there is very low QPU utilization in variational algorithms as well as in calibrations, in fact. And finally, quantum error correction is very difficult to implement and to be further developed with very long development cycle times. So it takes very long to iterate over quantum error correction experiments, and we must have better tools that allow exploring quantum error corrections and other applications from a flexible and highly productive software platform. And this is where QM comes into play. So at Quantum Machines, we're focused on the control stack of quantum computing. Our goal is to bring the best out of any quantum processor out there and allow achieving fastest time to results in quantum development. In our control hardware stack, we have a highly scalable and modular analog frontend, which produces the signals that drive the QPU dynamics. And then at the heart of our technology, we have our pulse processor. And this is a new type of processor that is designed for quantum control, and it's responsible for generating the pulses and the quantum measurements and sequencing and orchestrating the entire quantum program, as well as bringing in the classical compute resources. So this is the tightest integration of classical processing into the heart of the control hardware. This is actually the first control hardware that really integrates general classical processing that could be run in real time together with the quantum processing. Now the interface to the pulse processor is QA, our programming language, pulse level programming language. And this is a first of its kind programming language that allows programming the pulse processor again, which means it allows to program quantum and classical operations in the same code, so that they could be programmed and run together with precise timing control, and they can affect one another. Furthermore, we've integrated into our hardware many important components such as coprocessor, stream processing capabilities, high bandwidth networking, storage and caching, and more. All of which allow to integrate more general and heavier classical processing resources into the system in a seamless way. And this brings me to our software. In our software stack, we have entropy, our QPU abstraction, and execution flow management platform, which allows to start creating more complicated workflows of classical programs and quantum programs and create complex workflows from those. And our compilation stack that integrates us to higher layers of the stack, for example, our integration with OpenQASM3, which we're releasing these days. Okay, so let me give you some examples that demonstrate why this is so important and why this platform is so helpful. So going along our previous examples, let's start from looking at how this can dramatically speed up calibrations. So here's a nice example from the Lawrence Livermore National Lab. This is a typical Ramsey measurement that is used to characterize a qubit and calibrate its frequency. What you can see here is that with the typical control system that cannot perform classical processing to scan parameters very fast, they used to run this program in 900 minutes. Okay, so many hours. Now with the quantum orchestration platform, this actually takes 2 minutes. Okay, and in fact, this drop from 900 minutes to 15 minutes was because of classical processing that allows scanning pulse parameters very quickly. And the drop from 15 minutes to 2 minutes was due to another form of classical processing, which is responsible to resetting the qubits back to the zero state. So measuring qubits, understanding their states, and then controlling them to reset them to the zero state. And so this is significantly faster. And the implications of this are important because it runs so fast and because it runs in the control hardware itself, embedded in the control hardware itself, it allows us not only to calibrate much faster, but also to calibrate much more frequent, which maximizes system uptime and keeps the system calibrated at all times to the best performance. Okay, so this is fast calibrations, and they rely heavily on integrating classical compute resources into the control hardware. Now, the second example is that of enhanced QPU utilization. So here we look at the new CLOPS benchmark by IBM, and I want to thank IBM here actually for introducing this benchmark because the nice thing about this new benchmark is that it measures not only the QPU, but it really is a benchmark that starts to look at the control layer architecture and the entire system performance and how fast one could run sequences of programs on the entire system. And now these are preliminary results, but we've tested CLOPS with the quantum orchestration platform when the new benchmark was announced, and we were very happy to realize that due to the PAS processor, we can in fact perform the entire CLOPS benchmarking in our control stack, in our control hardware, without having to go out and access heavier classical compute resources, and thus allowing us to already be ahead of the game with CLOPS that above 10 kiloclops. So 10,000 clops. And this is just the beginning. We're testing it right now, and we're actually already in better results, and there is much more room for improvement due to our classical compute integration. All right, and finally, as a third example, I want to show you how easy and productive it is to program some of the most advanced quantum error correction protocols with the quantum orchestration platform while enjoying the best real-time performance in the market. So at QM, we have very important roots in quantum error correction. The first quantum error correction demonstration in history was actually done by no other than our chief engineer and one of the founders of the company, Nissim Ofek. So here you see the just how complicated it was to run this experiment. This is the control diagram of this demonstration. And this is just for a single logical qubit, not yet performing gates between logical qubits and scaling up to many logical qubits. And everything here runs with extreme hardware performance. And so if we want to push making faster progress with quantum error correction, demonstration was very difficult, took a long time. If we want to start shortening the cycle time of quantum error correction, we must allow to program these kind of protocols from a much more flexible and easy to use software platform without compromising on the hardware performance, because it's needed for quantum error correction. So one really great example we recently implemented that shows this is the magic state distillation protocol suggested by AWS in their December 2020 paper on cat codes, on concatenated cat codes architectures. I like this example, well, first of all, because magic states are very important in order to be able to perform certain critical gates on logical qubits that are quantum error corrected. And the other reason I really like it is that this protocol is quite complicated in terms of the control flow that must run in real time and the classical computing that needs to run in real time. So here on the left you see the pseudocode for the stop algorithm, one part of the magic state distillation protocol. And this involves a lot of classical processing and control flow, repeat until success loops, many complicated control things. And here you see the pseudocode, and the nice thing is that if we put the quacode that we've used to implement this right next to it, it really, really resembles a pseudocode. It's almost one-to-one with the pseudocode. And this shows that with Qua and with the pulse processor, you can really program these things very easily, the way you think about it, the way it's written in pseudocode in the paper, but it's going to run on the pulse processor in real time with best performance. In fact, feedback latencies that are best in the market, hundreds of nanoseconds of feedback time. And so this is actually broader than quantum error correction, because as we said at the beginning, the road for quantum computing is very long. There's so much more learning and exploration that we need to do in the next several years regarding how to best run calibrations, error mitigations, quantum error corrections, applications, that it's not good enough to just build a very specific hardware that maybe can do one thing very optimally, but lacks the flexibility that we need. Because new ideas are going to come up all the time, they're coming up all the time, and they require new underlying capabilities from the control stack. And we must have a flexible platform that allows us to shorten the cycle time of trying out new ideas, learning from them, and repeating this process many, many times. And again, this is really about trade-offs between extreme hardware performance and software programmability and productivity. And I hope that I was able to convince you that quantum machines were pushing towards exactly this with our quantum orchestration platform and with our tight integration of quantum and classical processing. And with that, I want to thank you, and I'll be happy to take any questions.